সেই 4:30 থেকে খিদে পেয়েছে, ওইটুকু ম্যাগিটাই ভাগ বসালাম, কি খাবো মনে হচ্ছে।
কেউ এখনো জয়েনই করে। ও পড়লে ওরা পকাপক তুমি খেয়ে নিত।
ফোনতে বলে খাচ্ছে, আমি খিদে পাচ্ছে অন্যদিন হলে দেওয়া যেত, আজকে আমি প্রচুর খিদে পেয়েছি, তাই করতে উঠেছি।
এই তো একটা এসছে, শুরু করি। All right, so we'll start today's session. So it's the fourth session of this live session is regarding the organometallic chemistry and its principles and applications with the aid of transition metals. Hello everyone, I am Anubhav Nath. I am a PhD scholar from Department of Chemistry of IIT Kanpur. So today I'll have some basic sets of problems regarding this siege activation and basic problems and some preliminary ideas that can help you out in understanding the prelim basics. So we'll start. So first question is the reaction of dihydrogen with Wilkinson's catalyst. You all know, you have heard about or read about this Wilkinson's catalyst, that is rhodium pph3 whole 3Cl is a rhodium plus 1 compound. Okay, so whether it's to form a 6 coordinate complex is a option 1, this is a ligand isomerization reaction. Option 2 is the oxidative addition. Option 3 is the beta hydrate elimination, and option 4 is the reductive elimination. So first of all, you all need to know how these reactions are classified. So what is ligand isomerization, what do you mean by oxidative addition, or what do you mean by beta hydrate elimination or reductive elimination? So all these reactions are actually very much prominent and very much well known in the field of organometallic chemistry. So coming to the answer, the correct option is option 2, that is oxidative addition of the Wilkinson's catalyst. So let us have a look on how it goes. So here is the mechanism. So this one is Wilkinson's catalyst, the first one. So rhodium pph3 whole 3Cl. So rhodium plus 1 compound because pph3 is a neutral donor and chloride is an ionic donor. So rhodium 1 is a d electron, a d8 system. So it is 8 electron. 3 pph3 are all donating 2 electrons each. So 3 into 2 is 6, and this chloride is a 2 electron donor. So it is 8. So 8 plus 8 is counting towards 16 electrons. So firstly, when it is subject to the catalytic cycle, you can see it's a reversible reaction where one of the pph3 goes out. So neutral donors have a tendency to just eliminate or dissociate from the molecule to generate a vacant site or an empty site so that the substrate molecule can attack or bind here. You can see from this chloride cannot go out, because if chloride goes out, the rhodium's plus 1 state will go away. It will not remain in a plus 1 state. Nevertheless, this pph3 is actually, if it is a neutral donor, and if it goes away, it remains in its rhodium 1 oxidation state. So that's why between chloride and pph3, it's pph3, one of the pph3 molecules that goes out. Now, if this pph3 goes out, there is a vacant site that is created in the rhodium center. Now, if we put this hydrogen molecule into it, that's a question, is the reaction of dihydrogen with Wilkinson's catalyst. This hydrogen molecule is oxidatively added to this rhodium molecule. Now you can see these two hydrogens are oxidatively added to this rhodium 1 to form a rhodium 3 species, because these two are hydride. All the hydrides are actually -1 in charge, mononegative in charge, and it's a 1 chloride. So this is rhodium plus 3. So from rhodium plus 1, we are going to rhodium plus 3. Remember, in every case, in each and every case, whenever an oxidative addition is occurring, the oxidation state of the metal is increasing by 2 units. In all the cases, if it is a metal 0 oxidation state, it will go to metal plus 2. If it is in metal plus 2 state, it will go to metal plus 4. If it is in rhodium plus 1 state, it will go to rhodium plus 3 state. Now, since this dihydrogen is a non-polar molecule, you can see it's a non-polar molecule, but this is a homonuclear molecule and linear molecule, and it is non-polar, and non-polar molecules get oxidatively added to any molecule in a cis fashion. That's why these two hydrogen molecules are cis in orientation. But whenever this oxidative addition, the molecule is oxidatively added, that is going to get oxidatively added, is polar, such that methyl chloride or methyl bromide, that is CH3Br or CH3Cl, then this oxidative addition takes place in the trans manner. Then this CH3 and this Cl, or the other part, this bromo or chloro, that remains in the trans manner of the molecule. But since dihydrogen is a non-polar molecule, it gets oxidatively added in cis manner. That's why from rhodium 1 to rhodium 3, we are generating a rhodium dihydride species, and the two hydrogens are cis to each other, not trans. Okay. So the first question is was regarding how these Wilkinson catalysts behave in presence of dihydrogen. So let's come to the second question. It's regarding the agostic interaction. Now the question is the presence of agostic interaction is best determined by which of these techniques. The first option is the magnetic susceptibility. The second option is UV visible spectroscopy, or its mass spectrometry, or the neutron diffraction. So the correct option is option 4, that is the neutron diffraction. So before going to get the details about how this neutron diffraction takes place, you have to know what do you mean by agostic interaction. So here is a classical molybdenum molecule, that is molybdenum PCOI3 whole 2 CO whole 3, that's featuring an agostic interaction. So here you can see, like with molybdenum, there are two PCOI3 molecules are actually bound, and the other three molecules are CO. Now you can have a count on the you can have a count on the total valence electron of the complex. Now you can see this molybdenum is a 6 electron species, D5S1, and this all the CO molecules and this PCOI3, all these ligands are 2 electron donor. So we have 5 such ligands. So 5 into 2 is 10, and molybdenum is 6 electron species. So total it's a 16 electron species. Now, to have a clear idea how this agostic interaction takes place, you have to know what this interaction is, or how this interaction will take place. Whenever any such ligand that will possess a CH bond angular to it, or to the ortho group or the meta group that is close to the metal atom, that will undergo a field interaction with the metal. So, for example, in this molecule, this PCY3 group has 3 cyclohexyl group. This C6H11 is the cyclohexyl group that is abbreviated as CY. That's why it is abbreviated as CY. So these CY molecules have this carbon, this carbon, this carbon. All these 5 carbons have 2 hydrogen atoms each. Now, for your convenience, I have actually depicted one of the CY groups in the broken bond. That is, it is containing 2 hydrogen atoms in this carbon, and these hydrogens are actually proximal, or they are actually close in field to this molybdenum atom. Now this hydrogen atom is having a field interaction with this molybdenum, and this carbon atom is also interacting with the molybdenum to form a 3-centered 2 electron bond. You can see this is a carbon, this is a hydrogen, and between this carbon and hydrogen there is a 2 electron bond. Now the molybdenum and is also engaging itself with both the hydrogen and the carbon. That's why we are having 3 centers. One is the molybdenum, other was in the hydrogen, and the other is the carbon. So there is a 3 center, but electron number of these centers are 2, because only this CH bond has 2 electron. All these bonds are actually not a perfect bond, but an interaction in the space. That's why this agostic interaction is actually a 3-center 2 electron bond, when these 2 electrons is delocalized among these 3 centers, 3 heteronuclear centers: molybdenum, carbon, and hydrogen. That's why this acidity of this CH bond gets enhanced by multiple folds, because you can see this CH bond is now dragged towards this metal, so the CH bond becomes weaker. That's why the acidity of this CH bond becomes enhanced. That's why in such cases, when we have to confirm whether it's an acoustic interaction or not, neutron diffraction is one of the best techniques, where we can clearly see in X-ray like this hydrogen is actually interacting with the molybdenum atom or the metal atom. So there are some salient features of this interaction. Firstly, this is the MH bond. M is here the molybdenum. So M can vary from molybdenum, from titanium or zirconium or vanadium or chromium. So this MH bond distance is typically lying in the range 1.8 to 2.3 angstrom. The MHC angle, that is the MHC angle, this angle is actually lying in from the range from 90 degree to 140 degree. And lastly, as I have said, there is a comparatively upfield shift of the 1H NMR, because you can see this is a hydrogen and this is actually getting interacting with the metal atom. That's why it is getting some hydridic character, that is a negative charge accumulation is taking place on the hydrogen. That's why the NMR shift is actually going upfield. So if this hydrogen is typically coming in the range 1.2 ppm, it will now come in the range zero point 0.5 or zero point 0.3 ppm or zero point 0.4 ppm. So that's why in case of acoustic interactions, the metal hydride species are actually denoted, and the upfield shift of the proton NMR is noted. That's why we can confirm, how we can confirm whether this hydrogen is actually going to undergo the acoustic interaction or not. The third question is regarding this again, this Wilkinson catalyst, this RHCl PPH3 whole 3. So the question is rationalize the fact why, unlike RHCl PPH3 whole 3, that is the Wilkinson's catalyst, IRCl PPH3 whole 3, that is the higher analog of the rhodium, is not catalytically active for alkene hydrogenation. This iridium is actually the heavier congener of rhodium from the cobalt group. Cobalt, rhodium, then it's iridium. Okay. So now this iridium ClPPHC whole 3 undergoes actually cyclometallization reaction to give rise to this HIRCl PPH3 whole 2. One of the phosphine groups is actually now gets activated, and we form this species PPH2C6H4. I'll show you how this is happening. A coordinatively saturated iridium 3 complex that is not catalytically active anymore. So to elaborate the fact, this is the structure. Here you will understand on a better point. So this is a iridium ClPPHC whole 3, that is the heavier analog of the Wilkinson's catalyst. It's a 16 electron species. Now, if we treat it with dihydrogen, now instead of producing a dihydride, we will have the cyclometallated species. We will have this cyclometallated species. Now, how this happen actually? Iridium is now from going here from 1 to 3 as rhodium was going. Like in the previous slide, I have shown you like rhodium was also going from 1 to 3 by forming dihydride. But in case of iridium, since it's a 5D metal and the nephroxetic effect or the field effect of iridium is much higher than that of rhodium, because the principal quantum number of iridium is higher than that of rhodium. That's why in case of this molecule, one of the phosphine groups is actually gets activated. So you can see here I have picked up this phosphine. So one of the phosphines is actually this one, and other phosphine groups are pH2 I have shown. So now one of the ortho position of this phenyl group gets activated in presence of the metal. That is the CH bond of this phenyl group actually gets activated in presence of iridium 1. And that's why this carbon and this hydrogen, this carbon and this hydrogen is actually gets oxidatively added to the middle center. That's why from iridium 1 we are going to iridium 3, and this CH bonds hydrogen is going to here. That's why since this CH bond is actually non-polar or very less polar, I have already told you like non-polar bonds gets oxidatively added in cis fashion. You can see this hydrogen and this carbon is also in the cis fashion. That's why since in this case the ortho position of this phenyl group gets bound to the metal, that's why it is called orthometallation. So it is since we are obtaining a cyclometallated product, this is cycle that we are having 1, 2, 3, 4 actually members. So if it is a 4-member cycle, one of the member is metal, other is the carbon, and one is the phosphorus. So it is actually a type of cyclometallization reaction where the metal center is so much having this field effect. That's why it's activating one of the ancillary ligand CH bond, and it gets bound to iridium to produce the cyclometallic species. The 16 electron species, we are going to an 18 electron species. Such is not the case in case of rhodium complex. In the rhodium complex, it is also coordinatively and electronically unsaturated, but in that case it is capable of binding to a substrate, that is alkene or dihydrogen. Thus the rhodium complex remains as catalytically active. It does not produce such cyclometallic species in presence of this catalytic cycle. But in case of iridium, it is actually going from 16 to 18. Now you can see it is a coordinated compound which is 18 electrons. So it is electronically saturated. It is also coordinatively saturated. That's why it cannot perform any catalysis. That's why it is actually dumb or inactive towards the catalytic cycle. That's why in case of Wilkinson catalyst is actually this rhodium compound is actually well known, but it is such iridium congenate is not known for catalytic hydrogenation of alkenes. So coming to the next question, it is regarding the calculating the valence electron of the complex. I have already told you like valence electron count is very important for this course. You have to know how to actually calculate the valence electrons. So the question is this eta 3 C8H13 iron POMe whole 3, that is also under whole 3, plus BF4 minus. This is the complex. This is quite a big complex, large complex. So you have to have a note how these ligands are orienting around this iron atom. So state whether there is an agostic interaction is present in the molecule or not. So here is the explanation. So you can have a look on it. So this is the structure of the molecule where this is the C8H13. So for your convenience, I have already told you this is a C8 molecule, cyclic 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms are there, and it is eta 3. So 3 carbon atoms are actually bound towards the iron. Now, since we are having a BF4 minus, that's why this metal complex is positively charged. That's why the counter anion will be affecting. Now, you can see there 3 carbon atoms are here, and like 3 carbon atoms are actually well known for the ligand allyl. That is, we call eta 3 allyl. Here also, it is an eta 3 allyl, and the eta 3 allyl groups are actually 4 electron donor and mononegative in charge. That's why you can see if we take, for example, this PMe whole thing, this ligand is neutral. So we are having zero electronic charge contribution towards the metal. So if you assume this iron's oxidation state is X, and we are having a negative charge from here, so X minus 1 is counting towards the plus 1 charge of the complex. So X plus minus 1 is counting towards the plus 1 charge of the complex. That's why uh, it is having X is minus 1 is going to the other side of the equation. So X is actually plus 2. So the oxidation state of iron is plus 2. So iron is a 3d8 4s2, iron is a 3d6 4s2 metal. So iron plus 2 is d6. So 6 electron from here. So from here it is actually where I have already told this eta 3 allyl is actually 4 electron donor. One is from the alkene group, other is from the negative charge. So 6 plus 4 is 10, and we are having 3 POMe3 group. All the OMe3 POMe3 groups are 2 electron donor, so total 6. So we are having 10 plus 6 is 16. So this is 16 electron species. Now this 16 electron species, in this case, in all the cases you have to know the other part of the question is whether an agostic interaction is there in the molecule or not. So in agostic interaction, it is not mandatory that the CH bond will be cleaved or will be permanently broken from the carbon, but it may be weakened in the form of an agostic interaction. So here you can see at the crystal structure of the molecule, this carbon hydrogen bond, this carbon is actually nothing but this carbon, that is the adjacent carbon to this allyl group. So we are having 2 hydrogen atoms in this motif. Now one of the hydrogen atoms is actually proximal or near or close to the metal center, that is the iron. That's why this hydrogen is having an agostic interaction with the iron. That is, it is a classical example where you can see a late transition metal, that is such as iron, is actually taking part in an acoustic interaction. In most of the cases you will see the early transition metals, that is titanium, zirconium, vanadium. These are the molecules that is actually undergoing the acoustic interaction. But this is an example where you can see a late transition metal, that is 3d6 4s2 configuration metal, 3d metal iron, that is undergoing, you can see here, is with the ch bond there is an interaction with the metal center. So this is an acoustic interaction where which actually leaves this ch bond weakened. The ch bond is not permanently broken, but it is having a significant amount of interaction with the metal center because of the proximity effect. So for your hint, actually I have given a hint for electron count. This iron 2 is a 6 electron. Allyl group, this is the allyl group, it is having 4 electron. And we are having POMEC group, and we know that any phosphine group is actually 2 electron donor. So that's why this compound has this structure, and it is a 16 electron species. So you see this compound is actually electronically unsaturated because it is still able to accommodate two more electrons. That is 18 electron count is not actually fulfilled here. So it is electronically unsaturated. So coming to the next question, here it is showing some classical examples of CH activation by transition metal complexes. So here you will see how this CH bond gets activated to transition metal complexes by simple bonding. Now here is the three actually examples I have taken to show you how this CH activation may takes place. So here the let's come to the example number one. So this is an iridium species. We are having a CP star ligand, and we are having two hydride ligands and one PME3 ligand. So firstly we will have the electron count. So this is actually three mononegative ligands. So iridium is actually plus 3. So iridium 3 is a D6 actually configuration metal. So all this CP star minus is actually 6 electron donor. You know that CP minus are 6 electron donors, eta 5 CP minus ligands. And this CP star is actually I am saying because whenever these hydrogen groups are actually substituted by methyl groups, we assume it or count or assign it by CP star. From CP to CP star because it is CP methyl. So both CP and CP star are actually 6 electron donors. These three ligands are 2 electron donors. 3 into 2 it is 6. 6 plus 6 from this CP star is actually 12, and from this iridium it is actually having 6. So total it is an 18 electron species. Now from this, if we actually enlight it by H nu, and this one of two hydrogen molecules get eliminated, and the external reagent is carbon methyl whole 4. Now what happens? So you can see, you have to know these dihydride species are actually quite unstable in nature, metal dihydride species. And whenever we are putting some light or irradiating a metal dihydride species or metal CO or carbonyl species, elimination occurs. So here is two hydrogen molecules which are cis to one another are reductively eliminated. It is called reductive elimination. Now we know that is the oxidative addition is actually responsible for the oxidation state increment of plus 2, such as this reductive elimination is also responsible for the reduction of the metal by plus 2 unit. So it is iridium 3. So from iridium 3 we are going to iridium 1. So here two hydrogens molecules are eliminated. So we are from formally we are from going iridium 3 to iridium 1 because from reductive elimination two hydrogen molecules are eliminated. Now they are actually putting this external reagent CMe whole 4. Now this CMe whole 4 has what you can actually think about it like it has a carbon and 4 methyl groups. Now one of the methyl groups has a CH carbon or CH bond. Now you know these iridium compounds are actually very much prone to oxidatively cleave this CH bond. I have shown you in the earlier example in the Wilkinson's catalyst slide when this carbon, this phosphorus or this pH group is actually gets oxidatively cleaved, and we are having a cyclometalated complex. So here is also happening the same. This CH bond gets oxidatively cleaved and this gets oxidatively added to the iridium center, and again we are going to now from iridium 1 to iridium 3 because from this we are having minus charge, from this carbon we are having minus charge, and from this hydride we are having one minus charge. So this is actually iridium 3. and this carbon center is actually gets added. This is a neopentyl group that is added to the metal center, and in this we are having a hydride molecule. So from this 18 electron species, we are actually arriving at this 18 electron species, because we are actually putting this reagent into the reaction mixture. This is CMe whole 4, so that the oxidative addition is happening, and we are having a metal monohydride and a metal carbon bond. So this is an organometallic species we are actually producing, where two organometallic entities are there. One is a CP star, and another is the neopentyl group. This is a classical example from this scientist Bergman in 1982, where he has shown this entire mechanism. So coming to the next example, this is the Cp iridium CO whole 2. So let's again count the electron. This iridium 1 complex, because Cp minus we are having a negative charge, COs are neutral, so iridium is positively charged. So iridium plus 1 is a D8 system. So 8 plus 6 is 14, and from these two carbonyls we are having 4 electrons. So it is actually an 18 electron species. Now in 18 electron species, again they are irradiating it. This H nu is means irradiation. So again they are having this irradiation H nu, and they are putting a pressure of methane of 10 bar. So you have to know this atmospheric pressure is 1 atmosphere or 1 bar, but 10 bar is quite a high pressure. So they are actually pressurizing this compound, and they are actually enlightening or irradiating it, and then they are pressurizing it with methane gas. This methane, this C6F12 is nothing but the solvent of the reaction. This is nothing actually. They are actually putting these F groups because they do not want to hamper the hydrogen molecules of the solvent. That's why they have taken this fluorinated solvent, so that these molecules are stable in the solution. Now I have already told you, under irradiation the CO molecules also get eliminated. They are photolytically cleaved. Now this is the case when this iridium is actually one of the CO molecules are getting eliminated. One of the CO molecules are getting eliminated. So we are left with one of the CO molecules is if get eliminated, then we are having a vacant site here. So for example, let's take these CO molecules is actually eliminated. So one of the vacant sites is actually methane. Now methane gets oxidatively. So methane has a vacant coordination site to get attacked to the metal center. That's why this CH bond gets activated, and we're actually arriving from iridium 1 to iridium 3 center. So one iridium hydride molecule, and another is the iridium carbon, the organometallic species. Now so we have to think like in this manner. So whenever we have to perform a CH activation, whenever we are going to perform a CH activation, we have to actually create a vacant or empty space or site in the metal environment, so that the substrate molecule gets bind or activated to it. That's why in first case also they're actually irradiating with H nu to get these hydrogen molecules eliminated. In the second case also they are irradiating it to get one of the CO molecules get eliminated to bind to the methane. That's why this is a work of Graham in the next year, actually 1983, where these iridium hydride and iridium carbon balls are actually present, and they are actually obtaining this iridium 3. So it is D6, it is 6, so 6 plus 6 is 12, and from these three ligands are having 2 electrons. So 12 plus 6 is counting towards 18 electrons. So from 18 electron, we're actually arriving at 18 electron species. So coming to the next work by Whitesides. So when we are having a platinum complex. So this is actually a platinum plus 2 species, one hydride, one carbon, it's a neopentyl group, and another is the cyclohexyl PCY diphosphine ligand, chelating ligand. So when they are uh, actually thermally, so here is the example. In the both the examples, photolytic activation of the metal center happens. It is the thermal activation, where 45 degrees Celsius temperature is actually put, and you can see these two bonds are actually reductively eliminated to to produce this CMe whole 4. This carbon and this hydrogen, these are actually cis to each other, so that's why reductive elimination takes place. And this elimination of this molecule takes place. Now they are giving the cyclopropane substituted cyclopropane molecule to see how it actually acts. So here you can see these carbon hydrogen groups are blocked by methyl groups. So only one or two CH bonds are here. So one of the CH bonds gets activated by the platinum 0 center, and we are actually from going from platinum 0 to we are going platinum plus 2. So one hydride as the cyclopropanyl group, propene group is their cyclometallic group. So is another example where this late transition metal is actually involved in activation of the CH group. This is the work of Whitesides in 1986. So these are the actually three great scientists who have actually discovered this CH activation, and they have performed several reactions to show how these transition metal complexes are actually involved in CH activation. So coming to the next question, so it is regarding the plausible alkane binding modes to the metal center. So here you can see these are all the possible modes of binding to the metal center. So here the first one is the eta 1 hydrogen mode. Here you can see only one of the hydrogen CH bond is actually gets attached to the metal center, so other hydrogens are not involved actually. So this is a metal single eta 1 hydride. It's eta 1 because only one actually atom is responsible. So it is the eta 2 HH mode where two hydrogen atoms are actually get cyclically bound or interacting with the metal center. The two hydrogens are spectator here. It's the eta 3 mode where three of the hydrogens of the carbon is actually getting interacted with the metal center. You can see 1 2 3 and one is a spectator. It's not doing anything, it's just sitting there. Another one is the eta 2 carbon metal interaction. Here you can see these CH bonds, the CH sigma star bond is actually interacting with the metal center, and the metal is not actually interacting with any other of the CH bond. And the last one is the most popular one that I have actually talked about earlier, how this agostic interaction. Here you can see the CH bond is actually having an interaction with the metal center, but the carbon is also having an interaction. So this is actually a three center two electron bond where these two bonds of the CH bond is actually gets resonance or gets used by the three centers. There's hydrogen, carbon, and the metal. So all the bonds become weakened in nature. This CH bond becomes weakened, and we call it the agostic interaction, where the carbon is also having a significant kind of interaction with the metal. Same is the case of this one. These are only difference being between these two. The carbon center is not actually having any interaction with the metal center in this molecule. The next question is how this CH activation takes place, stating about the Bergman type of CH activation involving late and nucleophilic complexes. Now, let's talk about this Bergman seed activation via late nucleophilic complexes. So here, the late actual molecule, late nucleophilic complexes are actually those one who are lying in the late transition metal elements. So here, in this case, you can see from the diagram, this is the metal d orbitals, and this is the CH sigma orbitals. We are having a pi back donation that is very large than the sigma donation. So from metal to the CH sigma star, the pi back donation is taking place, but the sigma donation is quite less because the sigma electron density of the CH bond is quite low. So for example, actually it ends up in getting the oxidative addition of the product. That's why this CH bond gets oxidatively added. We are actually left with the metal carbon bond here, and is the metal hydride. This is an hydrido alkylo alkyl metal complex. We are actually in Bergman type of siege activation. We are actually having the oxidative addition. Now coming to the salient features of this Bergman type of siege activation. So you can see about first. Let's talk about the regioselectivity. How these are actually handled. So the order is sp2ch greater than 1 degree sp3ch greater than 2 degree sp3ch very greater than 3 degree sp3ch. So both the kinetic and thermodynamic preference is there to form the least sterically hindered CM bond. You can see the sp to CH bond radioselectivity is the highest for this metal hydrogen bond strength. So as accordingly, you can also tell that the SPCH is the most higher prone towards this CH activation. Now, the kinetic preference is that the activation barrier to sigma complex formation is lower for less statically hindered CH bonds, that with the most S character. You can see these sp3 carbons are actually least electronegativity in the series, and the sp carbons are actually most electronegative, because sp carbons have S character of this 50% and they are linear in nature. That's why sp carbons are actually least statically hindered and most electronegative in nature. But the sp3 carbons are actually having three carbon atoms surrounding it, so it is sterically the most hindered one, and the S character of sp3 carbon is only 25%. That's why it is also least electronegative in nature. So from 50% electronegativity we are reaching towards 25% electronegativity, and from this linear molecule that is sterically least hindered, we are going to the most statically hindered, that is the tetrahedral molecule. Now that's why these sp or sp2 carbon hydrogen bonds are tending towards this Bergman type of CH activation faster than the sp3 CH bond. Now the thermodynamic preference is also there, and it is also favoring the same order, because like I have already told, the electronegative atoms are actually those ones who are forming most strong ionic bond with the electropositive metal. Now since these sp or sp2 carbon atoms are more electronic in nature, that's why they are forming more ionic bond with the metal center. You can see we're having a more ionic bond with the metal, and the carbon are having a bond. So depending upon the stability of the bond, it will be predicted from the S character of the carbon which bond will be formed. So in case of sp or sp2 carbon atoms, the electronegativity factor is more. That's why the electronegativity difference between the metal and the carbon center is most in case of this sp or sp2 carbon in the left side. That's why they are forming a stronger carbon metal bonds, so we are having a stronger bond. But in case of this sp3, we are having a less strong bond, that is a weaker bond of the carbon metal. So that's why the order, both the kinetic and the thermodynamic preference, is actually lying towards the favor of this sp or sp2 carbon hydrogen bonds. That's why regioselectively, if we talk by regioselective manner, the sp or sp2 carbon hydrogen bonds are oxidatively added to the metal center faster than the sp3 carbon hydrogen bonds. So both the kinetic and the thermodynamic preferences are there. The kinetic preference, I will again tell you, the activation barrier to form less sterically hindered bonds is more less. Kinetic preference is actually that one which will see whether this molecule is having a preference or not. So if you are having a hindered carbon hydrogen bond, it will not be formed. But if we are having a less sterically hindered bond, it will be formed readily. So both thermodynamic aspects and kinetic aspects are actually favoring this order. So we will continue this talk in the next slide. In the next slide, let's say, let's say so we are having a metal. I have depicted iridium and rhodium. So metal, it is actually bound to cp star, two hydride molecules and one pme3. So I have already told you, whenever we are thermally or photolytically exciting it, we are producing the elimination of the dihydrogen molecule. So in case of that, the hydrogen molecule is eliminated, and its L is nothing but a 2 electron donor. It can be Pme3. So we are having left to the 16 electron species. So from this 18 electron, we are going to a 16 electron species. Same is forming in case of this molecule also. This is Cp star MCO whole 2. I have already told you about the earlier examples how these molecules react under photolytic or thermal case. The CO molecule gets eliminated, and we are having left with these 16 electron species. Now you can have a look at a line: low oxidation state metals capable of donating electrons in sigma bond formation, they are highly prone towards air oxidation. So here we are having a metal one state, the metal one state. So M1 states are actually very much prone towards aerially getting oxidized. So air is containing a 20% of oxygen, and this is a metal one center. So this one center will undergo oxidation by the aerial oxidation or the oxygen. Now, since this is a low electron, low oxidation state, so metal is having a high charge accumulation on itself. That's why they are actually prone towards donating the electron to the sigma bond of the CH bond. Now since they are electron rich and we are actually putting this carbon, this actually alkane, 1 2 3 4 5 6, this is the hexane molecule we are giving. Now this hexane molecule has a CH bond, and since this metal is actually electronically rich, you can see this is coordinatively unsaturated and electronically also unsaturated intermediate. Electronically unsaturated, why? Because it's a 16 electron species, which is actually still having to prone towards the 18 electron count, and we are having this Cp star is actually blocking the three coordination sites of the metal, and this is actually having one coordination site, so only four coordination sites are blocked but two are actually still vacant. That's why this intermediate is quite unstable, because it is coordinatively and electronically unsaturated. Now we are having putting this hexane molecule here. This CH bond gets interacted with the metal center. This is a proposed sigma complex intermediate. Now this CH bond gets activated and we are having this carbon actually bound to the metal center and this hydrogen bound to the metal center. Since this is oxidatively added, metal is going from 1 to +3 oxidation state. Now, these hydridoalkyl metal complexes are prone to non-productive reductive elimination in the presence of oxidants and non-productive protonolysis in the presence of protic reagents. You can see this is a metal hydride species, this is a metal carbon species, and now this molecule, if it has nothing to fade about, nothing to go produce, or reaction is nothing going out, it will again get reactively eliminated. Now, several examples have been actually put to see how these CH bonds are actually gets activated by this rhodium center and is the iridium center. You can see several CH molecules are actually notated: benzene, cyclopropane, N-hexane, 1 degree or 2 degree, propane 1 degree, 2 degree, cyclopentane or cyclohexane. So here you can see the relative rate of addition is highest in case of benzene, because in the earlier slide I have told you sp2ch bonds are more prone towards gets activated because kinetic and thermodynamic preferences is lying in it, because it is more electronegative in nature. That's why you can see the relative k is 19.5 here, and in case of iridium it is 3.9. So no one in this table is actually as high as in case of benzene, because all these molecules are here: cyclopropane or cyclopentane or cyclohexane, all are sp3 carbon atoms containing alkanes. But benzene is an aromatic hydrocarbon which is having a sp2ch bond. That's why the relative rate of addition to the metal center is highest in case of this benzene. In other cases, all the cases, all are actually same. You can see the 2 degree molecules, when it is taken in N 2 degree, the relative rate addition is 0 in this case. So in case of propane, 2 degree is also there. I have already told you, like when the spherical hinderedness, the steric hindrance actually increasing, the rate of addition decreases. That's why in case of 2 degree molecules, the rate of addition is quite less. But you can see in case of other cases, that is the N-hexane 1 degree is primary case, or in the cyclopropane case, the rate of addition is quite high because they are actually sterically less hindered. So this is a case when this is a ruthenium compound we have taken, the dihyd ruthenium dihydride trans-oriented, and 4 ppH3 molecules are there. When it is treated with this excess amount of this alpha beta unsaturated carbonyl, so what happens? So in first case, when this ruthenium compound is actually, let's count the electron of the molecule. Ruthenium 2 is a D6 metal, and we are having 6 ligands, all the of which are 2 electron donors. So 6 into 2 is 12, and 12 plus 6 is 18. Now this 18 electron species, now we are putting excess amount of this alpha beta unsaturated carbonyl. Now this alpha beta sorry, so this alpha beta unsaturated carbonyl is putting in excess amount. Now what happens? So I have already told you, when more amount of substance molecules are actually put to the reaction mixture, the one of the neutral ligand, that is here in this case it is ppH3, gets eliminated. This is called a ligand dissociation. Now ligand dissociation takes place, ppH3 goes out, and this alpha beta unsaturated carbonyl compound via this double bond gets attached to this ruthenium 2. Now this ruthenium 2 is actually having 2 hydride molecules here. Now a double bond is here and a hydride is here. So you know what happens. This this olefin double bond is actually gets hydrogenated by this dihydride species. Now that's why the hydrogenation product is this a star molecule. So from an alpha beta unsaturated carbonyl compound, we are having a OAT group. We are actually going to the A star molecule. This A star molecule is getting eliminated. Now we are actually from 18, we are actually left towards this 14 electron species, ruthenium 0 compound, because from ruthenium 2, two hydrogen molecules are actually thrown out from the ruthenium 2. So we are having left with these 3 ppa is 3, 6 electron, ruthenium 0 is 8 electron. So 14 electron species. So you know this 14 electron species is quite unstable in nature and very much reactive. So you know what happens next. So let us assume what can happen next. We are putting excess amount of this alpha beta unsaturated carbonyl compound. Now one of this carbon hydrogen group and this oxygen group gets bound to the ruthenium 0 center. I have already told you that a low oxidation state metals are actually very much prone towards throwing its electron to the sigma bond of the CH bond. Now it is an sp2ch carbon. Now I have already told you, like, both the kinetic and thermodynamic preferences are actually favors this ch bond gets oxidatively added to the low oxidation state metal center. Now this ruthenium 0 is having an ancillary ligand of oxygen, and this ch bond is quite proximal in nature with the ruthenium 0. That's why this ch bond gets activated, and we are actually having this ruthenium 2 species, where the cyclometallic compound is here. Ruthenium 2 gets bound to the carbon center, and another is the hydride. I have already told that when the bond is non-polar in nature, the oxidative addition is cis in fashion. So here you can see this carbon and hydrogen are cis in fashion. So that's why in this case, from this 18 electron species, we are actually reaching towards the cyclometallic species. It's carbon actually bound to ruthenium, and another is the hydride. So we are actually having a ruthenium hydrido alkyl complex. So this is the question is the given evidence for the intermolecular sigma complex formation. So let's start with this. So this is a classical example again with rhodium. So how this we're actually how we will prove this intermolecular sigma complex is actually forming. So this same scientist Bergman has actually noted this reaction when this rhodium 1 compound, the rhodium 1 Cp star CO whole 2. This is actually again an 18 electron complex. This is a D8 system, and we're having 6 electrons here. So 8 plus 6 is 14, and we're having two carbon monoxides. So we're having this 14 plus 4 is actually going to the 18 electron species. Now this 18 electron species is actually treated under this photolytic excitation, H nu flash. Now it is actually kept under krypton at a very low temperature. It's a 165 Kelvin. You can understand it's a very low temperature, that is even lower than minus 100 degrees Celsius. So such low temperature is actually required to trap such kind of unstable intermediates. Now they are actually putting this CMe whole 4, the deuterium version of this CMe whole 4. So what happens? I have already told that this whenever these such compounds, 18 electron compounds, are photolytically irradiated, then one of the CO molecules gets eliminated. So creating a vacant site. So from 18 electron, we are going to a 16 electron species. This rhodium 1 compound again under krypton matrix and CO. The new stretching frequency of this CO is 1946 centimeter inverse. Now, whenever this compound is subjected to react with the CCMCD whole 4, the CD bond is nothing but the analog of the CH bond. So the CH bond gets activated, and just like the previous examples, from rhodium 1, we are going to rhodium 3. So this CD and this rhodium carbon bond is there. The neopentyl group is there. So it is the sigma complex where the rhodium 1 is interacting with the CD sigma bond. Now you can see the CO stretching frequency here is 1947. From 1946, they are going to 1947. And whenever this oxidative addition is complete, it is forming rhodium 3, and the CO stretching frequency goes up to 2008. So from 1946, we are going to 2008. So a significant increase or increment in the CO stretching frequency, as high as this is 54 plus 8, a 62 centimeter inverse increment in the CO stretching frequency is taking place. So how they have actually proved it is the matter of fashion. So this is the time repeated absorbance of the species they have actually denoted. So this is the species that is having a new CO of 1946. Whenever they are treating it with under Krypton matrix with the CCD whole 4, these are having a band at 1947 centimeter inverse. And when this process is complete, so they are having a peak at 2008 centimeter inverse. So the entire process you can see is actually taking just 1 second, 1 millisecond actually. So within 1.5 millisecond the entire process is complete. From rhodium 1 we're actually arriving at rhodium 3. Now, this only 1 centimeter inverse increment in the IR stretching frequency of the compound is actually giving a hint to the author that is the intermediate is going via a sigma complex formation. So here you can see whenever this is rhodium 1 and this is a new CO 1946. So there it is actually going to oxidatively added to the CCD whole 4, the CD bond of the CCD whole 4, CD3 whole 4. Now from oxidative addition, rhodium 1 is going to rhodium 3. That's why the oxidation state of the metal atom is getting increased. So you know the when the metal is electronically rich, then it will put its electron density on the pi star LUMO of the CO. So the more electron rich metal will put more electron on the CO pi star. That's why the more the CO bond will be weak and the less will be the new CO, that is stretching frequency, because stretching frequency is the parameter to denote how strong the bond is. Now since this rhodium 1 you are going to rhodium 3, that's why the electron density on the rhodium center is actually gets lost because it is going from rhodium 1 to rhodium 3. It is going to a higher oxidation state. So the electronically enrichment or the electronic push or accumulation of electron on the rhodium center is low in case of rhodium, in case of rhodium 3, but in case of rhodium 1 it is high. So from high electron density we are going to low electron density. So the throw of electron to CO is actually less in case of this product. That's why the CO stretching frequency is actually going to high from this low. So from 1946 they are going to 2008. So you can see they from a just a 1 centimeter inverse increment have actually asked or given the hint to the author that the rhodium is actually going to oxidatively added. That's why the electron density on the rhodium center is actually less. That's why it is putting its electron density very much less on the CO molecule. So the stretching frequency is increased only by 1 centimeter inverse. When the entire process is complete, they are actually having a 62 centimeter inverse increment in the new CO stretching. That's why this, so the data is actually quite prominent in nature. How this only 1 centimeter increment is actually very much crucial to tell you this intermolecular sigma complex formation is quite vivid in such molecule. So with this I'll end the session. Now if you, any of you have any queries regarding any of the slide, you can ask.